Welcome to The Explainer, everyone. Today, we're putting on our mathematical detective hats. We're going to dive into a topic that really separates the passive memorizers from the strategic thinkers. It's the absolute core of the Cambridge 0606 and 0580 mathematics syllabus, simultaneous equations. Now, I want you to think of an exam paper not just as a memory test, but as a chessboard. To win, you can't just react to whatever problem is sitting right in front of you. You've got to think 5 moves ahead, right? You need to anticipate the examiner's next mental move. A lot of students, they just overload their answers with raw mathematical facts but totally lack the analysis to apply them. Others just rush and they miss the command word requirements entirely. But today, we're going to transform how you approach these problems. We're decoding complex algebra by treating it as a dynamic, strategic game where you are always in control. Ready to become a math grandmaster? Let's get started.
I want to ground our session today with this really incredible quote from the late, brilliant mathematician Marianne Mirzakhani. She said, "The beauty of mathematics only shows itself to more patient followers." And honestly, this is so crucial when we talk about exam strategy. Math isn't just some chore. It's not a race to the finish line where you just furiously scribble down numbers and hope for a mark. It's a patient, highly strategic game of discovery. When you're staring down a complex Cambridge past paper question, the answer usually doesn't just jump out at you. It hides behind layers of variables. It requires you to make really calculated moves, observing how one variable affects another. By adopting this patient, analytical mindset, you'll actually find that those seemingly impossible problems have a beautifully elegant, logical path right to the solution. So patience really is your ultimate exam strategy.
Okay, let's take a quick look at our roadmap for today. We're going to cover the two-variable mystery, the elimination method, the substitution method, lines meeting curves, and finally, we'll pack up your algebraic toolkit.
Starting right off with Section 1, the two-variable mystery. A lot of times in math, and definitely in the real world, a situation just cannot be described by one single unknown factor. Think about it. If I tell you that two numbers add up to 10, well, what are the numbers? It could be 5 and 5, it could be 8 and 2, it could be 100 and negative 90. A single equation with two variables simply isn't enough to find the absolute truth. You're left with infinite possibilities, and that is the two-variable mystery. To pinpoint the exact values without a shadow of a doubt, we need more info. We need intersecting facts. Let's look at a classic real-world mystery from our source material. Imagine a taxi firm. They charge a fixed amount just for getting into the car, plus a certain rate per kilometer. We know a 3-kilometer journey costs $4.60, and we know a 7-kilometer journey costs $9.40. So the ultimate question is, how much does a 6-kilometer journey cost? To figure this out, we have to find two hidden values, the fixed fee and the per-kilometer rate. Let's call our two unknowns F and M. Now, if we only had the data for the 3-kilometer trip, we never figure out the exact pricing structure. But because we have a second journey to compare it against, boom, we can lock down the truth. We can build two distinct equations.
Here's another fantastic example. Say a school has two highly competitive netball teams, and they both end the season tied with 26 points. Team A got there with 6 wins and 8 draws. Team B got there with 8 wins and 2 draws. So, how many points is a win actually worth and how many for a draw? If we just look at Team A, we can write a quick equation. 6 times the points for a win, let's call it W, plus 8 times the points for a draw, let's call it D, equals 26. So, 6W plus 8D equals 26. But by itself, impossible to solve precisely. I mean, a win could be worth 3 points and a draw 1. That works perfectly for Team A. But wait, does it work for Team B? 8 times 3 is 24, plus 2 times 1 is 26. Okay, wow, trial and error actually worked out perfectly there. But listen, in a real exam, relying on trial and error is going to cost you precious time and marks. We're balancing two unknowns, so we need a systematic, guaranteed way to find them.
And that brings us perfectly to the most critical foundational rule you've got to memorize. It is the absolute golden rule of this topic. Two variables require two distinct equations. Dealing with 3 variables, you're going to need 3 equations. Think of variables like unknown weights on a set of balancing scales. One scale gives you the combined weight, but to figure out the individual weight of each item, you need a second, differently balanced scale. By comparing the two, you mathematically strip away the unknowns without ever having to guess. This rule is your guiding light. If an exam question asks you to find x and y, and you've only managed to build one equation, well, you haven't finished translating the problem yet. You have to hunt through that text for the second equation.
Moving on to Section 2, the elimination method.
Now that we understand the mystery itself, let's pull out the first major tool in our algebraic toolkit. I want you to treat these math steps exactly like strategic moves on a chessboard. Remember, this isn't just shuffling numbers around. It's about actively destroying one unknown so the other is forced to reveal itself. And this really highlights the strategic choice you have to make right at the start of a problem. Generally, you've got two main paths: elimination or substitution. Yes, you can use graphical solutions, but as the textbook points out, graphs often give you approximate answers, so they aren't heavily relied upon for exact algebraic proof. So how do you choose between elimination and substitution? Well, elimination is your best weapon for aligned linear equations where you can easily match up the coefficients, the numbers sitting right in front of your variables. Substitution, on the other hand, is absolutely perfect when one variable is already sitting by itself, totally isolated. Recognizing the state your equations are in, that's the very first step to thinking like a top-tier student.
Let's break down how this elimination strategy works step by step. The entire goal here is to manipulate the equations so that when you combine them, one variable is completely obliterated. Poof, gone. First, look at your equations. Are the numbers in front of the x's or the y's exactly the same? If not, you multiply one or maybe even both entire equations by a constant just to force them to match. Once those coefficients match up, look at their signs. You need to memorize this little mantra. Same signs, subtract; opposite signs, add. So if you have a positive 3y and another positive 3y, subtracting the equations means you get 0y. It's eliminated. If you have a positive 3y and a negative 3y, you just add the equations together to eliminate them. Once you make that move, your two-variable nightmare instantly collapses into a super simple, single-variable equation. You just solve for that remaining variable. But hold on, you're not quite done. You then take that brand new value and substitute it back into whichever original equation looks simpler. That gives you the final missing piece of the puzzle. It's precise, it's ruthless, and it's honestly kind of beautiful.
Next up, Section 3, the substitution method.
All right, time for our second tool. This method is incredibly powerful, especially when the examiner tries to throw a wrench in your plans with weirdly structured equations. Let's conquer the substitution method. Think of it as a mathematical Trojan horse. Here are your 4 steps to victory. Step 1. Find the weakest link. Look for a variable that is already alone or super easy to get alone and isolate it. You want the equation to literally say x equals something or y equals something. Step 2, and listen, this is the critical part, take that something, that entire expression, and substitute it into the other equation in place of that variable. If you accidentally plug it back into the exact same equation you just rearranged, you're going to end up with a completely useless statement like 0 equals 0. Not helpful. Step 3, like magic, you now have an equation with only one type of variable. Go ahead and solve it. Step 4, take your hard-won answer and substitute it back into your isolated equation from step 1, and boom, you found the final unknown.
Let's actually walk through a quick example straight from the source text so you can see this in action. Say we are given two equations, 3x minus y equals negative 10 and x equals 2 minus y. Notice anything right away? That second equation has already done step 1 for us. The x is perfectly isolated. It's literally telling us exactly what x is in disguise. It's 2 minus y. So we jump straight to step 2. We go to our first equation, 3x minus y equals negative 10, and every single time we see an x, we swap it out for its disguise in brackets. So 3 times x becomes 3 times the quantity 2 minus y equals negative 10. Look at that! The x is entirely gone. We expand the bracket, 6 minus 3y minus y equals negative 10. Combine the y's. 6 minus 4y equals negative 10. Move the 6 over, negative 4y equals negative 16. Divide by negative 4, and we discover that y equals exactly 4. We then take that 4, plug it straight into our original isolated equation, x equals 2 minus 4, which means x equals negative 2. And just like that, the mystery is solved seamlessly.
Moving right along to Section 4, lines meeting curves.
So, let's see how all this builds up to what I like to call the boss battle of the syllabus, nonlinear equations. This is where standard linear algebra takes a massive leap into complex geometry, and it's where the substitution method really flexes its muscles. If you can master this, you are genuinely thinking at a grandmaster level. But first, let's define our terms. A linear equation, like y equals 2x plus 1, only has variables to the power of 1. Draw it on a graph, and it forms a perfectly straight line. But a nonlinear equation? That involves variables that are squared, or multiplied together like xy, or raised to other powers. A classic example is x squared plus y squared equals 5. Geometrically speaking, these represent shapes, like sweeping parabolas or perfect circles. When a Cambridge exam asks you to solve a linear and a nonlinear equation simultaneously, they're actually asking you a really cool geometric question. What are the exact coordinate points where the straight line acts like a sword and slices right through this curve?
So how do we attack these curves? Well, elimination is pretty much useless here, because you can't just easily add a squared variable to a normal variable and expect it to magically disappear. We absolutely have to use substitution. Here is your battle plan. First, completely ignore the big scary curve equation for a second. Start with the simpler linear equation. Second, isolate one variable in that linear equation. Make it y equals or x equals. Third, take that expression and plug it right into the nonlinear equation. Now a heads up. This step often requires some really careful expansion of brackets, especially if you're squaring an expression like x plus 1. Take your time here. Fourth, once everything is expanded out, you gather all your terms onto one side of the equal sign to set it to 0. You will almost always be left staring at a quadratic equation. Then you just use your standard quadratic toolkit, either factorizing or using the quadratic formula to solve for your first variable. And remember, because a line can cut through a curve or a circle twice, you're typically going to find two different answers for this first variable.
Let's look at the actual result of one of these epic calculations from the text. We had a curve, y equals x squared plus 3x plus 2, and a line, y equals 2x plus 8. By taking the line, substituting it into the curve, factorizing, and solving, the math revealed that x equals -3 or x equals 2. We then plugged those x values straight back into our simple linear equation to find the matching y values. The result? Two completely distinct coordinate pairs, -3, 2 and 2, 12. And this isn't just abstract algebra, guys. This is geometric reality translated into numbers. The math is literally proving that the straight path intersects the parabola at exactly these 2 points in space. Seeing that connection? That's what really elevates your understanding.
And finally, Section 5, your algebraic toolkit.
Okay, we've covered a tremendous amount of ground today, from the foundational logic of multiple variables all the way to slicing straight lines through algebraic circles. Now let's consolidate the whole shebang into a practical, actionable summary checklist. This is your algebraic toolkit. This is the mental framework you're going to carry directly into your exams. The crucial point here is knowing exactly which tool to pull from your kit based on the unique geometry of the equations sitting in front of you. The graphical method? Phenomenal for visualizing intersections, but since examiners love testing precise algebra, its main drawback is giving approximate, unmarkable answers. Elimination? That's your rapid-fire tool for two linear equations, though it does require the foresight to multiply equations correctly to align those coefficients. And substitution? That's your heavy artillery. It's absolutely mandatory for tackling one linear and one nonlinear equation together. Just be highly disciplined because the algebra can get incredibly messy. Choose the right tool, save time, and secure those marks.
Now, I need you to pay incredibly close attention because this is a massive exam trap that catches thousands of students every single year. When you're solving a line intersecting a curve and you've finally done all the hard work of finding your two x values, you still have to find the matching y values, right? You have a choice. Substitute back into the simple line equation or the complex curve equation. Listen to me. Always substitute back into the linear equation. If you substitute your x value back into a nonlinear equation, especially one with a squared term like y squared, the math can actually spit out multiple possible y values. The textbook explicitly warns that this creates erroneous rogue values. These are basically phantom coordinates where the line doesn't actually hit the curve, but the math of the curve by itself suggests a point exists. It's a mirage. Sticking to the linear equation guarantees you only find the true intersections. So please, whatever you do, don't fall for the trap.
Well, we've armed you with the logic, the specific methods, and the traps you need to avoid. In the source material, there's actually this legendary problem about a circular piece of card where a smaller circle is removed, leaving an area of 209 pi and a combined circumference of 38 pi. I know, it sounds completely terrifying, but underneath it all, it's literally just a simultaneous equation waiting for a grandmaster to apply the substitution method. So how are you going to apply these tools to break it down next time you face it? Keep practicing, keep strategizing, and I'll see you in the next explainer.